All right, so welcome to the next screencast for Unit 3. This is ionic and molecular compounds, and today we're going to talk about VSEPR theory and molecular geometry. So we're going to take what we learned about Lewis structures for compounds and now go one step further with it. So our essential question today is, how do you determine the different shapes of molecules? So this is going to be Lewis structures and molecular geometry, the VSEPR theory, and you're going to see what VSEPR stands for in just a minute. So molecular shape plays a large part in determining the properties and the shape of an overall compound or the shape of a substance, a whole bunch of molecules bonded together, kind of what overall shape and what overall properties they have. So what is VSEPR theory? It is valence shell electron pair repulsion theory. I know that sounds like a lot, but basically we're going to talk about valence shell electrons. So we're going to look at our valence electrons, and we're going to look at how those pairs repel each other. They are all negatively charged, so all the electrons around the central atom arrange themselves so they can be as far away from each other as possible. They want to minimize their electronic repulsion. So you got to think of them as all being negatively charged. They all want to repel or get away from each other. So they're going to try to distribute themselves or spread out so that they're not next to each other. So in a covalent bond, the bonding electrons are localized around the nucleus. And we can think about the covalent bond is directional, having a specific orientation in space between those bonded atoms. Ionic bonds have the electrostatic forces, which have no specific orientation in space, so that's not really vital for your understanding of this material. So let's look at this one, for example. We're just going to jump right in and start talking about these. So I know you can't read this right here, but I'll read it or I'll tell you what it is when I move this out of the way a little bit. So let's just start looking at a compound. So consider beryllium bonded to two hydrogens. So beryllium dihydride. So only 4 electrons surround the beryllium atom. These electrons in the bonds to the two atoms have minimal repulsion when located on opposite sides of the structure. So you're going to have, this is why it forms this linear structure. They are going to try to get as far away from each other as they can. So instead of bonding like right up here and maybe right up here, they are going to try to spread out as far as they can to repel each other. So they go on complete opposite sides. So you end up with the beryllium in the middle and the two hydrogen coming off at 180 degrees. So we would call this a linear structure. And it has a bond angle of 180 degrees. So generally, whenever you have a compound, for the most part, that's going to have one central atom and 2 atoms bonded to the outside of it, it's going to form this linear structure. The next type of structure is called trigonal planar. If we look at BF3, so you have one central atom and there's 3 bonded atoms around it, they are going to spread themselves out. So instead of how we were drawing it yesterday, where you have 1 going up and then 2 coming out the sides, they're going to bend a little bit to try to get as much distance as they can between each other. And this creates what's called a trigonal planar structure, 3-dimensional structure, with a bond angle of 120 degrees. So if you have a central atom with 3 things bonded to it, this is the structure that it's going to form. If you have a central atom with 4 things bonded to it, like methane, CH4, this is going to form what we would call a tetrahedron structure. Now you have to remember that these things are 3-dimensional. So this drawing down here, what it is showing you is you're going to have a carbon in the middle and you would have 4 hydrogens coming off. So like one of them is coming out at you, one of them is going behind you, and then you would have the other 2 coming off. So the way that we draw it here is to show one of them is going up, one of them is coming out, and then in this plane, one of them is coming out at you because it is a 3-dimensional plane. And along this plane here, you have one sticking out the back. So that's drawing this hydrogen sticking out the back. That's just a way to show that that one goes behind and that one goes in front. So if you were to connect them all together, it looks like this pyramid shape, and this is what we call a tetrahedron. And the bond angle between each of these is going to be 109 degrees 0.5. So they spread, or 109.5 degrees. So they spread 109.5 degrees out away from each other, which is a little bit different than this, where they are only spread out, or they are spread out to 120 degrees. So anytime you see an atom in the center and 4 things bonded to it, it's going to form a tetrahedron, and you're going to have a bond angle of 109.5 degrees. Now, there are some kind of exceptions or extras when we think about tetrahedrons that prevent it from forming a full tetrahedron. So these next examples really are modified tetrahedrons. So let's look at ammonia, NH3. In this case, there's 3 bonded atoms, and there ends up being a lone pair of electrons. So you can see them up here, this lone pair of electrons. So you would have this unbonded pair of valence electrons at the top. So you can see them right here. So really, in this plane, there are 4 things present. So there are 3 bonded atoms and 1 lone pair. So there are still 4 groups, which is why it's a modified tetrahedron. So the lone pair is actually more electronegative, so it is going to have a greater electron repulsion than the bonded electrons. So this one exerts a little bit more repulsion. It wants to get a little bit further away. So that lone pair takes one of the corners and without being visible, but it's going to distort the arrangement a little bit. So it's not going to be a true tetrahedron because you don't have this one coming out the top. You have something that's more electronegative now on top. And so it changes the bond angle a little bit to 107 degrees. So you can see it still looks like a tetrahedron, but this lone pair is not going to have anything bonded to it. So it changes this bond angle a little bit, and we call this a trigonal pyramidal. So you're missing that 4th piece of the tetrahedron. This one right here is also going to be a modified tetrahedron. So we have water. You have 1 central atom bonded to 2, so you've got 2 atoms bonded, but you have 2 lone pairs of electrons. So you see here, it's still going to be a tetrahedron because I have the 2 hydrogens coming off, and I have the 2 lone pairs of electrons coming off on the other side. Well, those 2 lone pairs of electrons end up having more repulsion than these bonded ones, so it pushes them away a little bit more. So instead of having this type of a structure, these 2 right here are filled with the lone pairs of electrons. So you see how it's drawn right here with the 2 pairs of electrons at the top, or you've got 1 pair coming up the top, 1 pair going out the back, and all you're really seeing is this of what's bonded. So this would be what you would actually see is the oxygen bonded to 2 hydrogens, and it pushes them, it changes the orientation, it distorts the arrangement a little bit, and so it makes it bent or angular. We commonly will just say that it is a bent. So instead of a linear structure, it's going to be bent, and it's bent because of those 2 lone pairs. And its bond angle is going to be 104.5 degrees. So it's a matter of just figuring out what lone pairs you have, or if you have 2 lone pairs or you have 1 lone pair, what shape they form. So this table right here, these are all of the ones that I am expecting you to know. We are not going to get into any of the other geometries where you might see 5 things bonded or 6 things bonded. These are just the basic molecular geometries that I'm expecting you to know. And you can see they all vary by the number of bonded atoms and the number of lone pairs. That's the important thing to determine, to tell you, or to look at to tell you what shape they're going to have. So 2 bonded atoms with no lone pairs is linear. 3 bonded atoms with no lone pairs, that's trigonal planar. But if you have, and 4 bonded atoms with no lone pairs, that's tetrahedral. If you have 2 bonded atoms and 1 lone pair, you end up with bent. If you have 2 bonded atoms and 2 lone pairs, you also end up with bent. And then 3 bonded atoms with 1 lone pair is trigonal pyramidal. And so you can see how all of the bond angles are going to be slightly different. And the structures or the shapes, the molecular structures or the shapes are going to be all slightly different. So there's a table in your notes to fill out that go with this. So what's the basic procedure to determine the shape? You have to write the Lewis structure, and you figure out how many bonded atoms you have and how many lone pairs you have. If no lone pairs are present, if you just have 2 bonded atoms, it's linear. 3 bonded atoms, it's trigonal planar. 4 bonded atoms, it's tetrahedral. If you have lone pairs, you take the tetrahedral drawing, and it's either going to be bent if you have 2 lone pairs, or it's going to be the trigonal pyramidal if it has one lone pair. So it just depends on how many bonded atoms you have and how many lone pairs you have. So there are some more complex molecular structures. So as you go through these, you can go through and look at some of these extra examples, but I am not going to expect you guys to know that. So what I want you to do is do these examples. These are the 4 examples that we're going to go through in class. So I want you to try to do these practice problems before you come to class using the Lewis structure and then using the chart that we just went through. And then we will move on to polarity and melting points and boiling points from there.